Hello everyone, and welcome to today's video lecture on Bernoulli numbers and the zeta function. And in today's video, what we're going to do is prove the connection between the Bernoulli numbers and the values of the zeta function on the positive even integers. Namely, we're going to show that the zeta function evaluated on the positive even integers, so zeta of 2n, where n is a positive integer, which equals 1 over 1 to the 2n plus 1 over 2 to the 2n plus 1 over 3 to the 2n plus ... that this equals negative 1 raised to the power of n minus 1 times b sub 2n, where that's the 2nth Bernoulli number, times 2 to the 2n minus 1 times pi to the 2n all over 2n close parenthesis factorial. And so to prove this amazing formula, I'm first going to ask you to recall the infinite product expression for the sine function, which I derived in another video on this channel. And that says that the sine function, sine of x, can be written as the infinite product x times open parenthesis 1 minus x squared over pi squared, close parenthesis, times open parenthesis 1 minus x squared over 4 pi squared, close parenthesis, times open parenthesis 1 minus x squared over 9 pi squared, close parenthesis, times open parenthesis 1 minus x squared over 16 pi squared, close parenthesis, and so on, ... Now the first thing I want to do to this formula is get rid of all of those pi squared terms in the parentheses. So to do that, I'm going to substitute pi x for x. And so when we do this, we get sine pi x equals, substituting now, pi x times, open parenthesis, 1 minus the quantity pi x squared over pi squared, close parenthesis, times 1 minus the quantity pi x squared over 4 pi squared, close parenthesis, times, open parenthesis, 1 minus the quantity pi x squared over 9 pi squared, close parenthesis, and so on. So then sine pi x is going to equal pi x times, open parenthesis, 1 minus pi squared x squared over pi squared, close parenthesis, times 1 minus pi squared x squared over 4 pi squared, close parenthesis, times, open parenthesis, 1 minus pi squared x squared over 9 pi squared, close parenthesis, times ... And then the pi squared terms just cancel. So we're left with sine pi x equals pi x times, open parenthesis, 1 minus x squared over 1, close parenthesis, times, open parenthesis, 1 minus x squared over 4, close parenthesis, times, open parenthesis, 1 minus x squared over 9, close parenthesis, times, open parenthesis, 1 minus x squared over 16, close parenthesis, times ... And then I just want to get rid of that leading coefficient pi x, so I divide both sides of this equation by pi x, and I get sine pi x over pi x equals this infinite product. So now we have this very nice infinite product expression for the function sine pi x over pi x. And I would like to study its properties further by converting this product, this infinite product, into an infinite sum. Well, how can I do that? I can do that by taking the logarithm of both sides. Remember that the logarithm of a product of terms equals the sum of the logarithms of the individual terms. So we're going to do that now. We're going to take the log of both sides of this equation. Okay, so then we have the natural logarithm of sine pi x over pi x equals the natural logarithm of this infinite product expression. Okay, so now we'll apply the laws of logarithms. The logarithm of a quotient of two terms is just the difference of the logarithm of those terms. So that means that we'll have log sine pi x over pi x equals log sine pi x minus log pi x, and that will be equal to this infinite sum. So this will equal the natural logarithm of the quantity 1 minus x squared over 1 plus the natural logarithm of 1 minus x squared over 4, plus the natural logarithm of 1 minus x squared over 9, and so on. So I'll just move that log pi x term over to the right-hand side of the equation, so I'll have log sine pi x equals log pi x, and then I'll just write this infinite sum a little more concisely using sigma notation. This will equal the infinite sum indexed from k equals 1 to infinity of the logarithm of open parenthesis, 1 minus x squared over k squared, close parenthesis. Now I would like to simplify this expression even further by getting rid of the logarithms, and I can do that by differentiating both sides of the equation with respect to x. So when we differentiate both sides with respect to x, on the left-hand side, I get 1 over sine pi x, and then I have to apply the chain rule, so that's times cosine pi x, and then applying the chain rule one more time, that's times pi. And this will equal 1 over pi x times pi, plus the sum, index from k equals 1 to infinity, and now applying the derivative here, 1 over 1 minus x squared over k squared, and then one last instance of the chain rule, times negative 2x over k squared. Well, let's just quickly simplify the right-hand side by canceling those pi terms there. So then we'll have pi times cosine pi x over sine pi x equals 1 over x minus, now let me just pull out that 2 there, 2 times the sum from k equals 1 to infinity of quantity 1 over 1 minus x squared over k squared times quantity x over k squared. Now I'd like to get rid of that 1 over x term on the right-hand side, so I'm going to multiply both sides of the equation by x. So when I do that, I get pi x times cosine pi x over sine pi x equals x times 1 over x minus 2x times the sum from k equals 1 to infinity of 1 over 1 minus x squared over k squared times x over k squared. Well, cosine over sine is just cotangent, so I then get the left-hand side is pi x times the cotangent of pi x. And now looking at the right-hand side, this equals, the x's cancel, so 1 minus, and then I would like to pull that x into the sum, so I have 2 times the sum from k equals 1 to infinity of 1 over 1 minus x squared over k squared times now x squared over k squared. And now something really interesting happens, because I would like you to look carefully at that term in the infinite sum, that term 1 over 1 minus x squared over k squared. Because whenever you see the expression 1 over 1 minus something, you should think that's the sum of a geometric series. And here, our ratio is x squared over k squared. So 1 over 1 minus x squared over k squared is the sum of the geometric series 1 plus x squared over k squared to the first power plus x squared over k squared to the second power plus x squared over k squared to the third power plus dot dot dot. And this geometric series expression for the term 1 over 1 minus x squared over k squared will be valid for all x with absolute value less than 1. And the reason for that is that we know that k can equal 1. K is actually ranging from 1 to infinity. So we need the absolute value of x squared over k squared to be less than 1 in order for this geometric series identity to hold. So now I can actually write the expression as a double sum. I will have pi x times cotangent of pi x equals 1 minus 2 times the sum from k equals 1 to infinity of the sum from n equals 0 to infinity of x squared over k squared to the n, that's the geometric series right there, times x squared over k squared. Now, for those of you unfamiliar with double sums, please don't be intimidated by this expression. Doing double sums is a lot like doing double integrals. We work from the inside out. So let's unpack this double sum a little bit so we can see what we're dealing with. This will equal 1 minus 2 times the sum from k equals 1 to infinity of open parenthesis. And now I'll just write the n equals 0 case first. That's x squared over k squared to the 0. And now I'll write the rest of the sum plus the sum from n equals 1 to infinity of x squared over k squared to the n, close parenthesis, okay, that's the inner sum there, times x squared over k squared. Okay, so this is going to equal 1 minus 2 times the sum from k equals 1 to infinity of, and now I'm going to multiply in the x squared over k squared in the outer part of the sum. And in the n equals 0 case, x squared over k squared to the 0 just equals 1. So when I multiply that by x squared over k squared, I'll have an x squared over k squared plus the sum from n equals 1 to infinity, and now multiplying in the x squared over k squared here, this will now be x squared over k squared to the n plus 1. Close parenthesis. But now I can condense those two terms in parentheses together by writing that this equals 1 minus 2 times the sum from k equals 1 to infinity of the sum from n equals 1 to infinity of x squared over k squared to the n. I just have to change the exponent to bring those two terms together under the same sum. Well, we can further unpack what this double sum actually looks like by writing out a two-dimensional array of its terms. So in the leftmost column, I'm going to have k equals 1, k equals 2, k equals 3, and in the top row there, I'm going to have n equals 1, n equals 2, and n equals 3. Now this is obviously an infinite double sum. I'm just showing the first few terms. And as I said, when we do these double sums, we work from the inside out. So we'll start by fixing k equals 1, and I'll write for n equals 1, I have x squared over 1 squared to the power of 1. And then for n equals 2, I would have x squared over 1 squared to the power of 2. And then for n equals 3, I would have x squared over 1 squared to the power of 3. And of course, the terms in this row would be added together, and the row would extend infinitely as n ranges from equaling 1 to infinity. So now I've gone ahead and filled out the next couple of rows for k equals 2 and k equals 3, and just as these sums extend infinitely to the right, they also extend down infinitely as k itself ranges from 1 to infinity. Now, as I said, if we're working from the inside out with this double sum, we would sum up the first row, then sum up the second row, then sum up the third row. However, it's actually much more fruitful for us to sum this particular double sum column by column. And there's actually a theorem from analysis called Tonelli's theorem that guarantees that we can do this, we can change the order of summation and still obtain the same result. So I'm going to do that. I'm going to change the order of summation by writing k equals 1 to infinity for my inner sum and letting n range from 1 to infinity for the outer sum. And so we're going to now sum this column by column. So for that first column, I'm going to fix n as equal to 1, and I'm going to factor out an x squared from all of these terms to get that this column sum equals x squared times the sum ranging from k equals 1 to infinity of 1 over k squared. For the second column, I'm going to fix n equals 2, and I'm then going to apply that exponent to all these terms. So I'll have x to the fourth over 1 to the fourth, and then x to the fourth over 2 to the fourth, and x to the fourth over 3 to the fourth, and so on. And then I can factor out an x to the fourth from all of these terms to get that this column sum equals x to the fourth times the sum from k equals 1 to infinity of 1 over k to the fourth. For the third column, I'll fix n equal to 3, so I'll then apply that exponent and have x to the sixth over 1 to the sixth plus x to the sixth over 2 to the sixth, and so on. And then I'll factor out the x to the sixth from all of those terms to get that this column sum equals x to the sixth times the sum from k equals 1 to infinity of 1 over k to the sixth. Well, why am I doing this? What's going on here that's so awesome? Well, it turns out that the sum from k equals 1 to infinity of 1 over k squared is just equal to zeta of 2. And the sum from k equals 1 to infinity of 1 over k to the fourth is just equal to zeta of 4. And the sum from k equals 1 to infinity of 1 over k to the sixth is, of course, zeta of 6. And this will continue. So our next column, column 4, which I haven't written here, will of course be x to the 8th times zeta of 8. Column 5 will be x to the 10th times zeta of 10, and so on. So again, we found that pi x times cotangent of pi x equals 1 minus 2 times, here's this double sum, the sum from n equals 1 to infinity of the sum from k equals 1 to infinity of x squared over k squared to the n. We found that this expression equals 1 minus 2 times, open parenthesis, zeta of 2 times x squared plus zeta of 4 times x to the fourth plus zeta of 6 times x to the sixth plus dot dot dot. And that can be written more concisely as 1 minus 2 times the sum from n equals 1 to infinity of zeta of 2n times x to the 2n. So let me just put a box around this incredible identity, which is a very important result for us in this video, but we're not done yet. Because some of you may know or recall that there's also an infinite sum expression for the cotangent function in terms of the Bernoulli numbers. And that expression is the following. We have that cotangent of x equals the sum from n equals 0 to infinity of b sub 2n, where b sub 2n is the 2nth Bernoulli number, times negative 1 to the n times 2 to the 2n times x to the 2n minus 1 all over, open parenthesis, 2n close parenthesis factorial. So now I want to rewrite this formula for cotangent of x as pi x times cotangent of pi x, because by doing that, I can then compare it with this other formula for pi x cotangent of pi x that we just derived and establish a relationship between the Bernoulli numbers and the values of the zeta function on the positive even integers. So in this expression for cotangent of x, I'm going to begin by replacing x with pi times x. We'll then have cotangent of pi times x equals the sum from n equals 0 to infinity of b sub 2n times negative 1 to the n times 2 to the 2n times pi x raised to the 2n minus 1 all over 2n factorial. Next, we'll multiply both sides of this equation by pi times x. And when we do that, on the right side of this equation, we can bring the pi times x inside the sum itself. So then we get pi x times cotangent pi x equals the sum from n equals 0 to infinity of b sub 2n times negative 1 to the n times 2 to the 2n times pi x to the 2n all over 2n factorial. So I'll just put a box around this expression and bring it up here to the top of the screen. So we now have two expressions for pi x times cotangent pi x, one involving the zeta function and the other involving the Bernoulli numbers, and we can now equate these two expressions to derive a relationship between these two concepts, the Bernoulli numbers and the zeta function. So when we do that, we have that 1 minus 2 times the sum from n equals 1 to infinity of zeta of 2n times x to the 2n equals the sum from n equals 0 to infinity of b sub 2n times negative 1 to the n times 2 to the 2n times pi x to the 2n all over 2n factorial. Well, one quick simplification I'd like to make is because I have 2 to the 2n and pi x to the 2n, I'll just combine those things in parentheses, so that term will become 2 pi x to the 2n. The next item of note is that these two sums have different indices. On the left-hand side, my sum starts with n equals 1, and on the right-hand side, my sum starts with n equals 0. So I'm going to start by just revising this sum on the right-hand side so that I take care of the n equals 0 case separately. So the right-hand side of this equation becomes, starting with the n equals 0 case, b sub 2 times 0 times negative 1 to the 0 times 2 pi x to the 2 times 0 all over 2 times 0 factorial. And then I'll have the rest of the sum. So plus the sum from n equals 1 to infinity of b sub 2n times negative 1 to the n times 2 pi x to the 2n all over 2n factorial. And now we can simplify this n equals 0 term. B sub 0 equals 1. Negative 1 to the 0 equals 1. 2 pi x to the 0 just equals 1. And of course 2 times 0 factorial, that's just 0 factorial, that also equals 1. So this entire term just equals 1. Well, the 1 on the left-hand side of the equation and this 1 from the n equals 0 case on the right-hand side of the equation just cancel each other. So now we'll simplify further by dividing both sides of this equation by negative 2. And when I do that, I have that the sum from n equals 1 to infinity of zeta of 2n times x to the 2n equals negative 1/2 times the sum from n equals 1 to infinity of b sub 2n times negative 1 to the n, and here now I'll actually split the terms up. I'll write times 2 pi to the 2n times x to the 2n all over 2n factorial. So I'll just bring this expression to the top of the screen, and now I want to multiply the negative 1/2 into the sum on the right-hand side. And when we do that, we get that the right-hand side equals the sum from n equals 1 to infinity of b sub 2n times negative 1, and now note that the exponent changes because we're multiplying by negative 1/2, so negative 1 to the n plus 1 times 2 pi to the 2n, and I'll hold off on writing the times x to the 2n. I'll put this over 2 times 2n factorial, and then times x to the 2n. Well, why did I write it that way? Because now we can very easily compare coefficients in these two sums. Both of these sums are indexed from n equals 1 to infinity, but on the left-hand side I have zeta of 2n, and on the right-hand side I have this expression involving the even subscripted Bernoulli numbers. And so this equation implies that zeta of 2n must equal b sub 2n times negative 1 to the n plus 1 times quantity 2 pi to the 2n all over 2 times 2n factorial. Well, this amazing identity is the final result of this video, so let's put a box around that. And now I want to just test it out on a few cases where we know the values of the zeta function. So we already know, and you can watch my previous video on the Basel problem, that zeta of 2 equals pi squared over 6. We found that by other means. So let's test this identity and see if that produces the same result. So for the zeta of 2 case, we have to let n equal 1. We'll then have that zeta of 2 equals zeta of 2 times 1, which equals b sub 2 times 1 times negative 1 to the 1 plus 1 times the quantity 2 pi to the 2 times 1 all over 2 times the quantity 2 times 1 factorial. This will equal b2 times positive 1 times the quantity 2 pi squared all over 2 times 2 factorial. Well, b sub 2 equals 1/6, and this will multiply 4 times pi squared all over 4, and that just equals pi squared over 6. So amazingly, this formula does work. In my video on the Basel problem on this channel, we also showed that zeta of 4 equals pi to the 4th over 90. So to compute zeta of 4 using our formulas, we'll let n equal 2. We'll then have zeta of 4 equals zeta of 2 times 2, which equals b sub 4 times negative 1 to the 3rd power times the quantity 2 pi to the power of 4 all over 2 times 2 times 2, close parenthesis, so 4 in other words, factorial. Well, we have that b sub 4 equals negative 1 over 30, and this is going to multiply negative 1 times 16 times pi to the 4th, all over 2 times 4 times 3 times 2 times 1. And when we make the necessary cancellations, we then find that zeta of 4 equals pi to the 4th over 90. We'll do one last example. We saw that zeta of 6 in our previous video equals pi to the 6th over 945. So we'll let n equal 3. We then have zeta of 6 equals zeta of 2 times 3, which equals b sub 6 times negative 1 to the 4th times 2 pi quantity to the 6th, all over 2 times 6 factorial. And we know that b sub 6 equals 1 over 42. So this will be 1 over 42 times 1, positive 1, times 2 to the 6th times pi to the 6th, all over 2 times 6 times 5 times 4 times 3 times 2 times 1. And then when we cancel powers of 2, we find that this equals 1 over 42 times 4 pi to the 6th over, I'll just factor 6, so 3 times 2, times 5 times 3. Those are the remaining factors that survive in the denominator. And this will equal, now just bringing everything into prime factorization, 1 over 7 times 3 times 2 times 4 pi to the 6th over 3 times 2 times 5 times 3. Well, I have two 2's in the denominator and a 4 in the numerator, so those terms will cancel each other. And I'm left with pi to the 6th over, looking at all these factors here, 7 times 5 times 3 cubed. And that's going to equal pi to the 6th over 945. So I hope you all will be convinced that this formula works and that we have a way of calculating the zeta function on the positive even integers using the even Bernoulli numbers. Well, that's it for today. I hope you enjoyed this video, and if you did, please like or subscribe to my channel. Thanks again.